Second section is setting up a basic site-to-site tunnel. Now, the GRE tunnel that we're going to talk about first is not something that you will typically set up in most organizations because it's not a secure tunnel, but it is a tunnel. Then we'll get into section 3 on IPsec, which is the mechanism to secure your tunnel. And then finally, we'll talk about remote access VPN, which is what you would do from a client, like a Windows machine, a Linux machine, a tablet, or a phone. Then the summary, and then we'll be started. Now, there are 3 labs associated with this chapter that you will be turning in, and these are really important labs to do. I know I've said all the labs are important, and I'm starting to see you guys getting the labs done, and I'm glad to see that, but keep that up. But these 3 are especially important, especially this one right here on configuring a GRE tunnel over IPsec. And one of the problems is they kind of present this to you in a bit of a vacuum. They don't explain the commands very well, but I'll try to give you some flavor of that when we get to that a little bit later in the evening. So, any questions before we begin the discussion?
Bill, I was doing one of the practice exams, and it was for EIGRP with the different let's see, where the heck is it? It was the Scan Practice Skills Assessment PT, and it mentioned something about SVI interfaces on a switch. What does SVI stand for? What is it?
Let's take that offline. That's not tonight's discussion.
Okay, fine. We can do it later.
Okay, maybe at the break or right afterwards. We'll take it offline a little bit, and then I can talk about it. Okay, anything else before we get started? All right, then I'm going to go ahead and flip over to our screen on the PowerPoints. Second to flip over. And there's our slideshow. Okay, so here we go. So let's start by talking about what is a VPN, or actually what the objectives of the chapter. So by the time we're done with the chapter this evening, we will be able to have, or we will have, described the benefits of VPN technology, a virtual private network technology. We'll describe site-to-site and remote access VPNs. We've talked about those very, very little this semester, but you probably have a good understanding of what that is. We'll look at the purposes and the benefits of a general GRE tunnel, although we don't generally use GRE tunnels without some heavy-duty security. We'll get into the IPsec, which is how we actually secure the tunnel. And then we'll look at the protocol framework. Now, this is probably the hardest part of the chapter, understanding IPsec, because it is not a protocol, just the same way as OSI is not a protocol. OSI is a framework into which we can build into protocols, and it's kind of the same idea on a little smaller basis. We'll explain how we can use a Cisco product called AnyConnect to allow us to have remote access to a VPN-enabled network through either SSL or through IPsec. And we'll look at that as we go along. So let's start out by talking about what is a virtual private network, what it is, why we have it, what we do with it, and so on. First of all, one of the most important things to know is that when we want to connect our network to other if we want to connect our network to somebody else's network, maybe our own, maybe a corporate office to a branch office, maybe a partner to us, or whatever, one of the things we have to always be concerned about is how are we going to secure the traffic that goes over the public, the WAN, the wide area network. Now, if let's say, for example, the connection between our 2 networks, let's say it's a branch office to a headquarters office, let's say that connection is handled over a dedicated leased line. So you went to the phone company and you went out and are leasing a line that you basically, I'm not going to use the word own, but it's kind of like that. That's your line. Now in that case, the security doesn't have to be too severe because it's a point-to-point connection. Now, could somebody get into the middle? Because after all, you are going through a various large set of offices. So since we're going through a large set of offices at this point, we could consider ourselves on a private network all the way through. But that's not typical today. Typical today is we're going to run our connections either between our branch offices and our home offices, either through a public cloud such as the internet, or even a private cloud like an MPLS or a frame relay. Now, MPLS and frame relay provide us a certain level of security. In other words, they give us pretty close to that point-to-point connection we get on a leased line. So we may or we may not have to worry about the security between, between our local networks. But if we decide to use a public cloud like the internet, then all bets are off. We have to be concerned with privacy. So this is achieved by creating a virtual private network. What's a virtual private network? It's a point-to-point tunnel connection between the two endpoints. Now, virtual simply means that the connection between one end and the other doesn't really exist as a fixed connection. We're going over this huge public network. We may be going through hundreds, thousands of routers along the way. Doesn't matter. The routers at the two endpoints, or the security devices at the two endpoints, connect to each other via a secure set of protocols. These protocols create our tunnel. The tunnel is simply a mechanism, a very easy to understand mechanism, that any packet crossing into the tunnel, as soon as it enters the tunnel, that packet is encrypted with very strong encryption, very strong hash integrity, and so on. And as it travels through the public internet, that packet is visible. That packet could be intercepted, that packet could be copied, that packet could be modified, could be done a lot of things. But since the packet is protected by encryption and integrity, authentication, and anti-replay, anybody who intercepts the packet basically gets nothing out of it. It's extremely protected from unauthorized access. So that's what we're going to look at in this chapter. We're going to look at how do VPNs actually work and how do they actually behave. So let's start by first looking at a general process of a VPN. A VPN is used to create this end-to-end private network connection, and this connection can be established over any third-party network. So even if you were running over a frame relay MPLS private cloud, or even if you wanted to be extra careful and you did have a point-to-point connection over a leased line, you could still run over a VPN and the data would still be protected and implemented. To implement a VPN, a site-to-site, in this case VPN, obviously you need special technologies. Now Cisco would like you to use, for site-to-site, you should have a type of a perimeter defense system, either an ASA firewall or a router. And then your business partners will have either a matching router, or you'll have a matching firewall, or your home or your remote users will have the appropriate client software on their computers. The benefits of your VPN are, of course, going to be in the area of cost savings, because if we can utilize a VPN we don't have to spend the money on dedicated lease lines or frame relay or MPLS systems. So we can leverage our existing internet infrastructure, which is probably also going to be faster than what we could get for a more private solution. So it allows us to gain a bit of scalability as well. It's compatible with all broadband technologies. It doesn't matter how you connect to the internet. It doesn't matter how you connect to your cloud, because this occurs, and this is the important thing, VPNs occur at layers 3 and above. The connections, we've already learned, the connections between our internet and us, or between our frame relay and us, that's all layers 1 and 2. So VPNs occur at layers 3 and above. Generally, most VPNs occur, if it's site-to-site, it's a layer 2 VPN. However, there are some layer 6, which are your SSL VPNs, both site-to-site and remote access as well. Site-to-site VPNs allow you to connect to entire networks. So I could have, again, a branch office to a corporate office, a partner to us, or whatever it is. And nobody on either end on the local network knows there's an internet or a public network in the middle. Addresses are always in sync. File services are in sync. Printer services are in sync. Everything is synced. Internal hosts have no knowledge that the VPN even exists. And they don't even know that the VPN has been created. It's just, to their appearance, it's just there. There's just a network at the other side. That's all there is to it. Your end host, let's say a server or a workstation on one network, will send and receive normal VPN traffic, or I'm sorry, normal TCP/IP traffic, and that traffic gets routed to the VPN gateways, which are your routers. It's the VPN gateways that are responsible for re-encapsulation, encryption, adding the extra integrity protection, anti-replay, and so on. The VPN gateway sends it through the tunnel, through the internet, through to the peer VPN at the other side, where the process is reversed. Upon receipt, the peer VPN just strips away all the stuff that the other end added, dumps the packet just like it came off the originating network. Real straightforward, real easy. This is what a site-to-site VPN looks like. You have a VPN tunnel through your public internet, and then you have your terminating devices, either a router, a firewall, or a combination of two at both ends. So that's really all a site-to-site VPN is. Any questions on site-to-site? Very good then. In the remote access VPNs, this is what we use a lot of. This is where we can sit there at home, at an airport, at a hotel, at a coffee shop. Doesn't matter where we are, but we can be anywhere as long as we can connect to the internet. We fire up a VPN client on our computer. Now, any packets that come out of our computer never travel over the network in plain view. It's always either encrypted or integrity checked, or however you want to set it up. So remote access VPNs are what we, as the telecommuters, mobile users, consumer to business traffic, we use. It's a client-server architecture, meaning we're running a client and we connect to a VPN server, typically your router, but it could also be a device behind the router. We gain secure access by use of appropriate authentication credentials. And it's used to connect not an entire network, but an individual host to a network privately. Now, most of the time, you will need to have a VPN client software installed, either installed as a third-party product with Cisco AnyConnect, or many times you can use a browser using HTTPS, which allows us to take and encrypt traffic over standard SSL encryption. This is what a remote access VPN would look like, where we have a client that initiates our VPN connection through our public network to a VPN terminating device, your router, your firewall, your ASA device, or a server, whatever it happens to be. So that's really all there is to VPNs. VPNs are actually very simple. Now we get into a little more of the tough stuff. We'll get into the configuring. The first thing we're going to do is talk about a simple, plain, vanilla tunnel called a GRE tunnel. Cisco has created a protocol, and the protocol has since been adopted and enhanced by the Internet Engineering Task Force, by the IETF, as a way of creating a network interconnection. So this way, I could have a private IP on this side, let's say 192.168.0, and the same private IPS address, 192.168.0, and I can create a tunnel in between a public network. This public network can still carry traffic, but the two ends can be treated as though it was on the same network. So I can, a host, let's say in LA, can talk to a server in Cleveland, and we don't have to worry about NAT. We don't have to worry about any translations. We don't have to worry about networking. The downside, the biggest problem with this tunnel is it is non-secure. I'll repeat that. A standard GRE tunnel provides all of the ability of tunneling, but none of the advantages of security. The other big advantage of a tunnel is it allows you to have two networks on opposite sides of the tunnel that are not IP. So let's say, for example, in the old days, we had a protocol, a very, very powerful protocol called IPX. IPX was a protocol created by Novell NetWare, or by Novell for NetWare. Good protocol, but was primarily, and in fact almost exclusively, a LAN protocol. Even though it supported routing, it didn't play well on a wide area network because it's chatty. It's a very, very broadcast-oriented protocol. On slower networks, on slower wide area networks, broadcast can be the death of you. So IPX didn't play well on a WAN, but companies loved it. It was easy to set up. It didn't have a lot of the overhead that you have to have with IP. It had a lot of the characteristics. It had a lot of advantages. I could go on. So if I had an IPX network at two different ends of the world, I could create a GRE tunnel, an IP tunnel. IPX packets would come into the tunnel, be re-encapsulated into an IP packet. And you see that in the illustration. The IP packet would then put on a standard IP header. It would put on a GRE protocol header, a few fields for that. Send it down the pipe as an IP packet at the other end. All of the IP stuff would be removed, and all that would be left would be an IPX packet. So for either a way of creating a non-secure private network between two remote locations, or the ability to have a different protocol on each side of the tunnel, that's why GRE tunnels are still, although not very often, are still in use. The basic characteristics of GRE, generic routing encapsulation, are the concept of re-encapsulating a packet. We know what encapsulation is. Encapsulation starts at layer 7. The layer 7 payload is given a header. That is considered a packet. That packet is then passed down to layer 6. Layer 6 encapsulates that packet by taking the payload and header from layer 7, sticking it into another packet with a new payload header, passing it down to layer 5, where a new header is added and it's re-encapsulated again. When we get down to layer 3, normally layer 3, the datagram at layer 3, is then taken, which of course includes the IP header and the payload. The payload, of course, is the data and all of the headers of the above layers, of the 3 or 4 layers from above, however many layers had to pass through. It adds its own layer 2 header. Now, the way GRE, the way all tunneling protocols work is, instead of immediately passing the layer 3 IP packet down to layer 2 for encapsulation into a frame, it takes the layer 3 packet and loops it back through the protocol again, another layer 3 encapsulation. So we take the IP packet with its original IP header and re-encapsulate it with another IP header, only this time the IP header is specific to the tunnel and the way to determine how to get it to the other endpoint in the tunnel. Now, when we talk about IPsec in the next section, we're going to talk about how that re-encapsulation process then encrypts the payload, the second round of payload. But standard GRE does not do anything. It just simply takes the payload, the layer 3 IP packet, takes that IP packet, re-encapsulates it with another. It doesn't replace the existing IP header. It's like putting an envelope in another envelope. That's really all it's doing. It's putting an envelope in another envelope with a completely different set of header fields in it. So GRE has these following characteristics. Now remember, we're not talking about an encrypted tunnel yet. We're still talking about generic GRE, which is a re-encapsulation to build a tunnel but not encrypt the data going in. So the basic characteristics are, first of all, GRE started out as a Cisco tunneling protocol, but Cisco released it and the IETF has now standardized it. It uses a protocol, number 47, and that will identify to the routers on both ends that this is in fact a GRE tunnel packet and must be de-encapsulated appropriately. GRE encapsulation uses an additional protocol type field to support the encapsulation of any layer 3 protocol. We talked about that. Not only IP, but IPX, AppleTalk, SNA, or whatever it happens to be. GRE is stateless, which means it's a typical layer 3 protocol. Stateless means no flow control, no packet control, no sequence control. It just simply sends the packets. GRE does not have any security mechanisms. And of course, naturally, since we are adding a new layer of encapsulation, even though it's still at layer 3, we're adding another layer of encapsulation, which is 24 additional bytes. Therefore, it does require additional processing, and therefore it does have a slower throughput through our network. Now, this is all you have to do. So you're on a Cisco router. Let's say you're on router 1 in the illustration, and you want to create a GRE tunnel over to router 2. Now, what goes between router 1 and router 2 is a couple of public IPs. As long as you can ping the other end's public address, you can create the GRE tunnel. If you can see that address, you can tunnel to it. So the first step, all you have to do, again, from global configuration mode on router. This is router 1. So keep in mind, we're over here on router 1 in our network. So from router 1 on our network, all we have to do is start by creating a tunnel interface. We are actually creating a new virtual interface between the two routers. So we have to give the interface a name. By the way, we're going to talk about this in a second, but you have to repeat the process on router 2 to point back to router 2, to router 1. You can't create a one-way tunnel. A tunnel is always two ways. I have to create a tunnel to the other end, so router 1 to router 2. But router 2 has to create a tunnel back to router 1 or it won't work. The tunnel name doesn't have to be the same on both sides. The tunnel name is local. It defines the name of this tunnel from your end. So for example, let's say you have, I don't know if you've ever, if any of you guys have ever been to San Francisco, and you've ever gone through the BART tunnel under the bay. Well, let's imagine that it's the same tunnel, but as you enter the tunnel in San Francisco, there's a sign up that says you are entering the San Francisco tunnel, the San Francisco Bay Tunnel. At the other end, coming out of Oakland, coming back into San Francisco, the sign on the wall says you are entering the Oakland to San Francisco tunnel. It's the same tunnel. It's just what the name is from the perspective of router 1 or router 2. So the tunnel name is not critical. It's just that it needs to be identified. So we create a tunnel interface. In that tunnel interface, we designate that the mode of the tunnel, it's going to be a GRE tunnel, and it's going to use IP as its transport mechanism. In other words, we are going to be encapsulating IP packets into our IP tunnel. Now, if it was another protocol, like let's say IPX or something, you'd be tunneling with another protocol. Now, if you take a look just up above, you notice each of these routers has a public address associated with its interface. So on router 1, the interface serial 000 has been designated as public interface 209.165.201.1. But the tunnel, remember, the tunnel is considered an interface, and it has an address of its own. Typically, although it wouldn't have to be, I guess, but typically that will be a private IP of some kind. It's going to be a private IP address, probably a 192.168 or a 172 or a 10 or something like that. So notice the first thing I have to do is give the tunnel, my end of the tunnel, an IP address of 192.168.2.1 with the appropriate subnet mask, 255.255.255.0. Then the next two lines indicate the source and destination public IP. Now, if you go into the lab, for those of you that have done the lab may have already seen this, but if you haven't been in the lab yet, you'll notice that the instructions say, don't type in the IP address, but type in the exit interface, just like we did with routing protocols. The IP address of 209.165.201.1 is associated or is assigned to serial 000. In the tunnel protocol, you can indicate the source, either by IP address, or you can do it by interface name. So I could equally well in that statement say tunnel source S0/0/0. Now the destination IP must be an IP address because you don't, number one, you don't know what the interface is at the other end, and even if you did, it doesn't matter. The source can be a address or an interface name, but the destination must always be a IP address. And it's not a network address, it's the actual IP address assigned to your destination. Now in this case, it's somewhat not confusing, but it's somewhat misleading because the other end is on the same network as the destination's on the same network as the source. That's the way you're going to do it in the lab because we're not going to build a whole routed network in between. But if you had a routed network in between, you would have to indicate that particular address. So it could be 209.165.201.1 on one end, but on the other end, let's say it's 87.43.12.18. Doesn't matter, whatever the address, the public address is on the other side. Now notice the next two lines are we have to define a routing protocol, just like anything else. But in this case, the routing protocol is not used to route the packets. This routing protocol is specifically there to route the packets or to give you, let me rephrase this. It's a routing protocol that indicates that the tunnel network is up and running. Because notice on the tunnel we have a 192.168.2.1 on one end and 2.2 on the other end. So those are the same network. So what we're really doing is claiming that we have a network that exists, another network attached to our overall network. We absolutely do not want to define this through our default gateway network. So we have to define another network for the tunnel. So we've already created our OSPF or our EIGRP network, or maybe even BGP if you're into that, if you've set up for that. But you still have to have a network for the tunnel. You have to have a network entry in the routing table for just the tunnel. Okay, I just got a question asked. Do you need the subnet with the destination? No, you do not. No, you do not. All you need is the destination IP address. You don't need it because that's what you're really doing. You are configuring the tunnel. Notice you also don't need a subnet mask for the source address of the tunnel. The source address of the tunnel is the address, the specific IP address of the exit interface, or the actual exit interface name. The destination, you need the IP address, but you don't need a subnet mask. The reason you need the subnet mask is when you're defining the network. Because remember, what you're doing is you're building a private network inside of a public network. The private network is called the tunnel. So you create the private tunnel just the way you would create any other private network. Question, but does it require the subnet if you use the IP address of the source? No, you do not. If you use the IP address of the source, you don't need the subnet of the source, the public. Remember, public. The private tunnel, the private network is a virtualization. And we build that tunnel with the subnet so that the machine on the other end, by the way, you only have a 2-device network. You could technically use a subnet of /30, which only has 2 ports anyway. But because we have so many private addresses, it really doesn't matter. Yes, just the tunnel. The source and destination, you need to have a specific IP, and it doesn't care what. But it's not that it doesn't care what the subnet has been defined, and the routers already know how to use that correctly. Very good. That's an excellent question. Now, on the other side, you repeat the process. Take a look. The other side, we create another tunnel. Now, they called it by the same name. That's a good convention. If you're creating a tunnel, it's a good idea to call it on the same name on both sides. Doesn't have to be, but that's not a bad idea. Notice again, the tunnel mode matches. It's a GRE tunnel carrying IP traffic. This time, the entry point to the tunnel is tunnel 0, yes. The entry point to the tunnel is 192.168.2.2, because that's the entry point on the other side of the tunnel. The tunnel source is the router 2 public IP or the router 2 interface name. The destination is the public IP of router 1. And once again, we set up a routing network, a network router within the tunnel, just so that it's in the routing table. And that's really all you have to do. That's all there is. To verify a GRE tunnel, there's a couple of commands. Show IP interface brief. Remember, you've created a new interface, a virtual interface, kind of like what a VLAN is to a switch. It's a virtual interface. It's a virtual network. If you show your tunnel, it will show you the name of the tunnel. It will show you the IP address assigned to your end of the tunnel. And it will specify, of course, like all good interfaces, is it up or down? Now, obviously, if the other tunnel isn't in place, it's going to be down. You can also use the
time
show
is 19
interface
o'clock.
tunnel by itself, and it will show you a lot more of the details. And, of course, you always want to look at your OSPF neighbors just to make sure that everything is hunky-dory. Okay, any questions on the standard GRE tunnel? This is, again, a GRE tunnel is used very, very rarely anymore. You don't see it, but it's a good way to introduce the concept of creating a tunnel without getting into all the problems that we create when we want to encrypt and secure that tunnel. Okay, questions, comments? Okay, so now let's get into what we really want to start building, which are IPsec-based environments, VPNs. Now, the difference between an IPsec tunnel and a GRE tunnel is its security. In fact, an IPsec tunnel is a GRE tunnel, but instead of just encapsulating with a new IP header, it encrypts the old IP packet so that it can't be spied upon, or it can't be modified, or whatever. So IPsec is simply the mechanisms that we are going to use to create a secure tunnel. GRE is not a secure tunnel. It's a tunnel, but it's not a secure tunnel. We're going to create a secure tunnel. Okay, so the difference visually is not much. It still creates, you still have Cisco routers or Cisco ASA devices or other equivalent type of devices. By the way, IPsec is a generic, now it's not a protocol, but it's a generic set of protocols, which means in theory, actually in practice as well, that as long as I follow all the rules and I know how I'm setting up both ends, I could have Cisco stuff on one side and I could have non-Cisco stuff on the other side. And as long as I follow all of the protocols that I am using, and we use the same protocols, the same passphrases, the same keys on both sides, we should, theoretically, be able to have a very, very secure tunnel, even though we are not completely Cisco or anybody else. So the idea of an IPsec VPN is that we can now transport critical data, secret data, non-shareable data between two networks that have no idea that there's a WAN in between them, but yet everybody else on the WAN can't see the data. So IPsec, first of all, even a bullet point before the bullet points you see. The function of IPsec is not a protocol. IPsec is a framework into which we are going to use a whole bunch of protocols for doing different parts. That's where it gets a little bit confusing. So the IPsec functions define how a VPN can be configured in a secure manner. That's the first thing. It provides a framework of open standards, which means you don't have to have all Cisco hardware. You could have Cisco on one side, non-Cisco on another. IPsec defines the rules that the actual protocols will follow. It is not bound to any particular encryption protocol, authentication protocol, security algorithms, or any other keying technology. In other words, it can use whatever. Now, by the way, it can't use anything. There are some protocols that are established and well used, but we'll talk about them. It relies on existing algorithms, so you don't have to either learn new ones or enable new ones or buy new ones if you want. It's a network layer framework, which means it's protecting IP packets. So obviously, it protects everything from layer 3 up to layer 7. It's not protecting anything at layers 1 and 2. The good news is that all the stuff that people want to steal is at layers 5, 6, and 7, not at layers 1 and 2. Secures a path between a pair of devices, either a pair of gateways, which would be your routers or ASA devices at both ends, or a pair of hosts, or any combination of the like. All implementations of IPsec obviously re-encapsulate. The re-encapsulated header is in plain text so that it can still be routed over an existing IP network with no problems. And since it's a layer 3 re-encapsulation, doesn't matter what you're carrying it over. It works fine over any layer 1 and 2 protocol. So it's an ideal way of performing this function, and it was well thought out and well designed. Now, to some extent, there is some level of complexity to get this flexibility. With great flexibility comes great complexity. Get it? Kind of a paraphrase on the Spider-Man theme. I'm not seeing any LOLs on the screen right now, so I'll assume you're laughing in private. The following can be considered the summarization of IPsec. Number one, it's a framework of open standards. It provides the 3 big things we need for security. Confidentiality, nobody gets to look at our stuff. Integrity, which means if anybody grabs our stuff and tries to modify our stuff, we know at the other end and we don't allow it. And origin authentication. What that means is, did this packet really come from Bill Sachek? Or did it come from somewhere else? Did it really come from the gateway that it's supposed to? And last, IPsec is a network layer protocol, so it protects IP packets, but by definition, since an IP packet contains layer 4 packets, layer 3, layer 5 packets, layer 6 packets, and layer 7 packets, it is also protecting layers 4, 5, 6, and 7 by definition. So it's all about security. IPsec. The name even says it. IP security. It's all about that. So the major 3 components, and the third kind of a really important component, are confidentiality encryption. Encrypts the data before transmitting it. At the other end, it decrypts it. Integrity. Verifies that the data has not been changed in transit. So even, let's say I intercept a packet. I can't decrypt it, so I don't know what it says. But what if I grab the packet, I take the actual payload off, and I put on my own payload? As soon as I put my own payload off and send it, the other end gets it and goes, no, you changed the payload. I'm not going to accept that payload. So the whole packet is dropped. And lastly, origin authentication. Verifies the identity of the source of the data that is sent. It ensures that the connection is made properly. We will talk about IKE as a key exchange in just a moment. And the last thing is anti-replay protection, which detects and rejects replay packets. So what happens is, let's say you are sending a logon packet or an authentication packet. It's encrypted and it's authenticated, but I still suck it off and make a copy of it. Now, at some point in the future, I come back and I try to use that packet to authenticate. And it says, that packet was 5 hours ago. Why wasn't that packet? How did that packet get into the mix? So, CIA, confidentiality, integrity, and authentication, are what makes up security services, and IPsec does it extremely well. So for encryption to work, both the sender and receiver must know the rules to transform the message into its encoded form. So we do this with keys. You probably have taken at least one computer class at some point where the discussion of a public or private key, I know we discussed it in semester 1, a little bit in semester 2, although we were doing a lot of it in semester 2. We mostly talked about it in semester 1. But there are several ways of setting up an encryption key. The rules of the keys are what makes the type of keys. So without a key, you don't decrypt. Now, obviously, the better the algorithm, the more complex the key, the harder it's going to be to decrypt. Now, a little bit of history. I asked this of my class last night, so I'm going to posit it to you guys. And Robert, you're not allowed to answer the question because you were there in class last night. So here's the posited question. What is the first, who did the first recorded cipher text? Who created the first set of encryption protocols that have been recorded in history? They probably occurred even before that. But does anybody know who had the first instance of it? This is a Jeopardy question, guys. Anybody? Nobody? Okay, Michael's going to try to answer. Not here. Okay. All right. Well, all right. I'll give you the answer. It was Julius Caesar. It was, I believe that, I've got to go back and look at my history again, but I think they called it the Caesarian code. What it was a simple substitute cipher where he had a set of rules that says if I give you the letter A, if I want the letter A in the original message, I'm going to substitute the letter S. And the letter B will be substituted with the letter Q. And the letter R will be substituted, and so on and so forth, and so on and so forth. Now, what that meant was that when he wrote a message, you could look at the message and say, it looks like gobbledygook. And unless you knew what the substitution was, what letters substituted for what other letters, what cipher letters. So you needed the key. The key was the list of mapping. The key was the map between the letter A and the letter S, or the letter B and the letter Q, and so on. The other thing that Caesar did was he also came up with the idea that a cipher code, a substitute cipher code, could be broken if you had enough examples. If you had enough samples of the code, you could look for commonalities. And by knowing, like, for example, certain letters of the alphabet tend to be more dominant than others, and certain strings of letters tend to form certain words. So if you could get enough samples, you could reverse engineer the substitution code. The way to solve that problem is to change the code periodically. So this week, the letter A is substituted with the letter S. Next week, the letter A will be substituted with the letter B. And if you changed them up often enough, nobody could get, number one, they not only needed to have enough samples, they needed to know which key you were using. So you change the key all the time. You rotate the key. Ergo, the first ciphertext. Very, very simple. Nice piece of history there. Occasionally, I like to throw that in just to simply remember or remind myself that I was a history minor in college. Okay, there are two types of algorithms that are used to encrypt and decrypt. We have symmetrical and asymmetrical. You probably are very familiar with them. Symmetrical algorithms use the same key to encrypt and decrypt. You have one key to encrypt and decrypt, and both sides must have the same key. You'll sometimes hear symmetric algorithms referred to as shared key algorithms, where we have to have the same key. The three main examples, and the three examples that are, or the three protocols within the IPsec framework that supports shared key are DES and triple DES, 3DES. Both of those were originally developed by the NSA and are considered today to be very weak encryption algorithms. The key can be cracked. If you have enough samples of your ciphertext, you can reverse engineer the key out based on some good hacking tools that have been developed over the last 20-odd years. DES has been around since the 70s, so everybody's had a good long time to crack it. It was also in the days when we didn't have the supercomputers. So you can now utilize some very, very heavy-duty number crunching to decrypt both DES. Now, triple DES is a little harder because it takes DES and then encrypts it again, and takes that and encrypts it again. It does a triple encryption. But if you can encrypt the first one, all it is, it's just the same decryption algorithms, the same hacking. It just takes a lot longer because you have to do it 3 times. Ergo, we would prefer not to use, we in the industry try to discourage companies from using either DES or triple DES. The advantage to them, they are supported by nearly every device. A much more secure shared key encryption is AES. AES takes a seed key. You start out with a seed key, a seed phrase. And by the way, if you've ever set up wireless internet using 802 or WPA2, which is 802.11i, if you've ever set up wireless access using WPA2 and you set it up for, you're setting up the encryption protocol, you could use TKIP, or better yet, use AES. Give it a passphrase, there you go. AES, which is a 256-bit key, and at this point has never been cracked. AES has not been cracked yet. You have a very secure environment. So if your VPN devices at both ends support AES encryption, go ahead and use it. All three, DES, triple DES, and AES, are symmetric keys. You use the same key to encrypt and the same key to decrypt. That is usually considered to be a pre-shared key. The problem with shared key encryption is very simple. The problem is, how do I get the key to the other end? Or how do I tell it that, oh, this is your key or this is your seed that I want you to generate the key from? I can't send it in an email. I can't call somebody over the phone. I have to make sure that the key distribution method is also secure. How do I get the key to the other end? Well, that's the problem with shared key. So asymmetric keys solve the problem of key distribution by having a key pair. You have one key that you use to encrypt. You have a second key that you use to decrypt. The two keys are mathematically related, but they're not the same. Now, what I can do is I can create a key pair. Let's say you want to send me a super secret message, but you would need to encrypt it with a key I can decrypt it with. You're going to encrypt. I'm going to decrypt. You're going to encrypt it, send it to me. I'm going to decrypt it and read it. So how do I get you the key? Simple. I create a key pair, a public key and a private key. As the name says it, I hold the private key for me. I'm the only one that has the private key. The private key decrypts. The private key decrypts. The public key is only good for one thing: encrypt. You can't use the public key to decrypt, only encrypt. Then I send you the public key. So you call me up or you email me and say, hey, Bill, I need to send you the super secret message. Can you send me your public key? Sure, no problem. Here's my public key. You take my public key, you encrypt the message to me using my public key, and send it back to me. Now let's suppose the bad guy also has my public key, because at some point he said, hey, Bill, can I have your public key? And I say, sure, no problem. Here's my public key. He has my public key. He intercepts your super secret message. Oh, what's he going to do with it? And the answer is nothing. He tries to apply my public key against the message, and he gets nothing. It doesn't apply. Because the only key that will decrypt is the private key, which I have not given out. I have the private key. Everybody else gets my public. Now, if I want to send you back a super secret reply, the way I get the super secret reply is I have to get your public key. I get your public key. I encrypt it to you. You get the cybertext. You use your private key. That private key decrypts, and now we can communicate. I have your public, you have my public. You encrypt to me, I decrypt. I encrypt to you, you decrypt. Simple. This is, in fact, exactly how HTTPS and digital certificates. Now, a certificate, like is granted through a certificate authority on the internet, is your public key as well as a lot of other information, like how long that key is going to be in effect, who created the key, who the key belongs to, and some other stuff like that. There's more to the certificate than just the key, but the key is the critical aspect of it. The algorithm, the encryption algorithm that is typically used in VPNs using a public-private key mechanism is RSA. RSA is one example of that. Now, RSA is the same encryption standard we use on the internet today. That is considered to be. Now, is it the only asymmetric encryption algorithm? The answer is no, of course not. There are a bunch of others. But it's the one that's the most widely supported out there. Now, by the way, which one of the two do you think is stronger? Public key, public-private, or shared key? Which of the two is considered the strongest? A symmetric key algorithm or an asymmetric key algorithm? Anybody want to take a guess? Oh, I'm sorry, Robert, you had a question, and I just noticed your hand up.
Yeah, this might be related to your question, too. It seems to me if the public and private key are mathematically related, it is theoretically possible with the supercomputer to crack it.
Yes, it is.
Last night you said, obviously, the symmetric key is stronger than the asymmetric key, but is that because of the mathematical relationship between the public and private key?
I couldn't have said it better myself. That's exactly why. So asymmetric keys are not as secure as shared keys, because a shared key is just that. The only people that have the key are the ones that have the key. Since I am giving everybody in the world my public key, and because the public key is mathematically related to the private key, in theory, you could reverse engineer from the public key back to the private key. However, that said, the amount of computing power or what it is, and depending on the complexity of the algorithm, it would take you probably hundreds of thousands of hours or hundreds of thousands of cycles of computer time to get even close. And by that time, you rotate the key. Again, like anything else, one of the best ways to keep keys safe is to constantly change them. Why do you think we always ask you to change your password? Because by the time you would crack it, it's already changed. So a good cyber environment, that's why, for example, digital certificates that you get from the internet, a certificate authority, has a life expectancy. Now, the life expectancy is sometimes measured in days or weeks, but more than likely it's months or years before they change the keys out. Just because every time they change the key, you've got to then request a new public key, which can be a pain in the butt, and get the key installed, set it all up. Take some time and effort, but that's the idea. But yes, absolutely. Robert, you're exactly right. Symmetric is considered more secure. That said, there's no problem with asymmetric keys, because if you're using a complex enough key generator such as RSA, by the time you would have decrypted the key, chances are you'll have changed it. Does that answer the question? I think that brings it up pretty straightforward. Cool. So, here's a problem. How do we, in a VPN environment, get the keys to exchange with each other? Well, I just said, secret is better than public. But secret has a problem with key distribution. So let me present an interesting idea and tell me what you guys think of this one. How about the idea that I use a secret key, but we use a public-private key mechanism to exchange the secret key? We use a one-time, or a virtually one-time, public-private key pair. We exchange our secret key. Now, if somebody cracks the public-private key pair, unless they happen to catch the packet that had the secret key, there's nothing they can do about it. So, the best of both worlds is using a secret key for tunnel encryption and tunnel decryption, but we use a public-private key mechanism to exchange that secret key. And that's what Diffie-Hellman is all about. You're going to hear this a lot in VPN, and that is the Diffie-Hellman key exchange. The Diffie-Hellman key exchange is not an encryption protocol. It is another framework. It's a mechanism that we use to allow the two sides to negotiate their keys. So what we do is we can securely exchange our keys for encryption and decryption. So Diffie-Hellman allows the two sides to negotiate a shared key. Actually, they don't negotiate it, they just establish it. So we build a shared secret key, but we build it on the fly, sort of, kind of, with a seed. And we exchange it by a combination of public and private on both sides. So we use a public key exchange mechanism to help us create a shared key on both sides that will match up. Now, the explanation's a lot easier than the implementation. Trust me on that one. But is it a fairly decent concept? Do you get the idea that we are going to use this thing called the Diffie-Hellman exchange so that we can create a shared key on both ends? The shared key is what's going to do the encryption and the decryption, and it's going to take care of our data integrity and our authentication. So the shared key is what we really care about, but we got to get the shared key to the other end. Diffie-Hellman is what we're going to use to do it. So does that kind of make sense before I go on? Very good then. This is kind of an illustration of what happens during the key exchange. So what we do is, for Diffie-Hellman, we both have to get each other's. We create a public-private key pair. Now, there's a lot of ways to do that, and you're going to see that in the example in the book. But we're going to create a public key pair. So router 1 will get router 2's public key. Router 2 will get router 1's public key. And now they both have an encryption and decryption key. I will have the encryption key for router 2. Now router 2 will have the encryption key for router 1 and vice versa, which will then allow us to encrypt, transmit, and decrypt. Now, this allows us to create the shared key. The shared key will be encrypted, transmitted, decrypted, and then vice versa. And after a few minutes, now we have a shared key. Once we have a shared key, the Diffie-Hellman exchange is complete. Now, the second leg of our security example, let's go back a second. There we go. If we go back a second to our security framework, we talked about confidentiality, integrity, and authentication. The encryption, using a secret key to encrypt our data, is the confidentiality portion. Now, the integrity is what we use to verify that the data has not been changed or altered during transit. And that's integrity. What we use for integrity is called a hash algorithm. And there are, just like with encryption, there are several algorithms that can be used for hashing. Now, we have our secret key. So we take the secret key, combine it with the algorithm, and we then have a mechanism by which we can take a packet, apply the key and the algorithm to the packet. We create a hash, a numerical representation of that packet. We then send the packet along with the hash to the other end. The other end takes the packet and the hash, puts the hash to the side for a second, uses the same, it knows what the algorithm is, and it knows the secret key that was used. So it takes the packet, combines it with the secret key that it already knows, and the algorithm that it already knows, combines it together and basically duplicates the hash creation. So we have now a second hash, one that was created by the receiving end. The receiving end takes the hash it created, looks at the hash that it received. As long as the two hashes are the same, there is a reasonable assurance, and by reasonable, it's more than 99.999% assurance that the packet is the same. That's integrity. So this is the process that happens. So at the sending end, Gail creates a transaction that says, I want to pay to Jeremy $100. So they take the transaction, applies it with the hashing algorithm and the secret key, and comes up with this number. At the other end, somebody else comes to this guy and says, I want to cash a check. Looks at the check that says, wait a minute, the check's made out to Alex for $1,000. The keys don't match. Ergo, no, we don't. You don't get to cash that check. So the the protocols that we are going to use for hashing are called hash-based message authentication. This is the mechanism. Now again, the mechanism requires several, in fact, two parameters. The message input, the secret key, and it actually has a third element, which is the algorithm. So the hash-based message authentication code is the algorithm that takes the message and the key, munches it, and comes up with the hash value. This hash value is sent with the message, and the process is reversed. That's all there is to it. It's very straightforward. Again, inside it, thank goodness we don't have to write the protocols. They've already been written. All we have to do is implement them. The two algorithms that are most commonly used in HMAC are MD5 and SHA-1. Now, MD5 is considered to be a fairly decent, albeit not perfect, integrity algorithm, hash algorithm. It's a 128-bit shared key or secret key and a fairly decent algorithm. SHA-1 is a 160-bit key, a little bit longer key, and it allows you to use variable length messaging. So it works a little bit better than MD5. The problem with SHA-1, it's been cracked. So even though it works out okay, most companies today are now reverting. They will still use MD5, or they will use SHA or SHA-2. SHA-2 has a variable length key. You can have a 256-bit or a 512-bit key. Obviously, the longer the key, the more secure your hash algorithm, the more secure your hash, but the more complexity you're adding to the processing. So again, how much processing you're going to do versus how much security you think you need makes the difference. Okay, so what I'd like to do now, I'm looking at the time, and we're looking at about 7:30, and we're going to go till about 8:30. I do have a bunch more slides, and now I want to get into some more of the complexity. So what I'd like to do is take a break at this point. So let's take a short break, let's say until 10 to 8. That gives us a little more than a little bit more than 10 minutes. So I'm going to pause the recording.
Recording stopped.
And I'm going to give you guys a break for about 10 to 12 minutes. And in that time, you can go take a little bio break, get a cup of coffee, get a glass of water, or whatever you need. And I'll see you back here at 10 to 8, and that's when we'll get started again. Thanks a lot. I'll talk to you in a couple minutes. Robert, are you online? Ah, there you are. Hey, I just threw a link up in the chat window, and this is also for anybody else who's interested. I just threw a chat up. Robert was asking a question about SVIs, and I think I'll answer it right now. It's pretty easy. SVI is short for Switched Virtual Interface. An SVI, and again, I found a really good little tool out there. Switched Virtual Interfaces is what you use to effectively route between VLANs. You know that when you set up a VLAN, that creates a collision domain, and anybody on that particular VLAN can communicate with anybody else. But if you want to communicate between VLANs, you have to have a trunk between the VLANs, and that would allow you to then communicate between different VLANs. Well, you communicate over your VLANs through switched virtual interfaces. So that's what allows you to have inter-VLAN communication, whether you're going, if you're going to use a layer 3 switch. Now, if you're using router on a stick, that's different. Router on a stick doesn't do the same thing, or if you had multiple interfaces. So that's kind of what it's all about. I think the description that Chris Bryant put up in the link I gave you, I think will, inter-VLAN routing and a layer 3 switch. That's exactly what a switched virtual interface is all about. So I want to make sure I covered that with you before we ended this evening. Okay. I hope that answered the question. Thanks. Any other questions before I turn the recording back on again? All right, then. I'm going to go ahead and hit the recording button. So we'll get back to starting.
Recording started.
Okay, welcome back. We're going to finish up the discussion of IPsec security with discussing the last couple of pieces. The next one is authentication. Now, obviously, if I want to connect one end of a tunnel to another end of the tunnel, each end had better make sure that the other end is okie dokie. So, for example, I don't want, let's say it's my office in LA to my branch office in Irvine, that is okay as long as the branch office knows that it's trying to connect to the home office, and the home office knows that it's trying to connect to the branch office. So we need to make sure we authenticate that both sides. And again, it's called a peer authentication. We're generally much more familiar with what's called one-way authentication. One-way authentication is I log on, so the server makes sure I know who you are. So when you log on to a server, you log on to a website, you have authenticated with the server. But how do you know? How do you know that's the right server? How do you know that somebody's not trying to pull your cyber leg? And that's the problem with one-way authentication. In a peer or two-way authentication mechanism, not only would I have to log on to a server, the server would have to prove to me that it's the actual server who it is. Now, to some extent, this is done with certificates. The way that is done primarily is with certificate authorities, and that's part of their function in addition to setting up the encryption and integrity algorithms. So IPsec virtual private networks support this authentication, this two-way authentication process. There are two ways to authenticate. The first way is with a pre-shared key. Now, this is a key that is different. This is not the same key we use for encryption and decryption. This pre-shared key is more like a password. All of you guys have set up a wireless network at home. So where you set up a router, and on the router you set up WPA or WPA2. And in that, it asks you to create a passphrase. Now, any client that wants to connect to the wireless has to know what that passphrase is. That's a pre-shared key. It's the secret key shared between the two parties. And that key is passed using a secure channel before it needs to be used. Now, this is used, so in other words, we've established the tunnel. We've established the encryption in the tunnel. Now we need to authenticate, and that's where this comes into play. Now, Diffie-Hellman allows us to create the keys that we're going to use for encryption and for encryption and integrity. This is specifically a key for authentication. So you go to the router on router 1 and put in the key, go to router 2, put in the same key. So that's one way to do it with PSK. Pretty easy, pretty straightforward. Most people do it this way. If you have control of both sides, if you can log on to both routers, if you can configure both routers or both devices, pre-shared key is generally the easier way to do it. The other way is with an RSA signature. Now, this is what, again, is happening on the internet. An RSA signature is effectively a certificate granted by a certificate authority. Now, you can be your own certificate authority, by the way. You don't have to go with a third party like VeriSign, because they'll charge you money for a certificate. So, digital certificates are used to exchange and authenticate your peers.
The time is 20 o'clock.
RSA is what you would use if you're going to have people that are not necessarily under your control, or devices that are not necessarily under your control. And again, it uses a public-private key mechanism to deal with it. So it's similar in nature to what's going on when we are using the Diffie-Hellman to generate the key exchange. But it's a little bit different in the fact that we are doing a third party. This is almost exactly what goes on when you go on to an HTTP-based website that requires you to log in with a username and a password. Now, within the within the IPsec framework, we're back to the framework again. What we are going to use to gain our confidentiality and security is very important. Remember the concept. Remember what we're doing with packets. A layer 3 packet gets to the router. A layer 3 packet gets to the router. The packet is unencrypted and has a standard IP header. The router's IPsec framework is going to have to do some work with it. It's going to encrypt, or it can. It's going to need to encrypt the payload or encrypt the packet and set up the integrity check. It's got to do those two things. We assume we've already been authenticated, and we assume we already have our non-replay already in place. You'll see that in the next slide. So now we have to determine, do we care if the packets are encrypted with integrity, or do we care if there's only encryption and no integrity, or do we care if there's only integrity and no encryption? So we have three options. Integrity only, which makes sure the packet hasn't been intercepted and changed. Encryption, which means nobody can read it, but somebody could still technically change it. Or do we want both? Depending on which of the three we want is how we configure the two ends. So if we configure the ends for just an authentication header, what we're doing is we're saying, okay, create the hash, append the hash to the packet, send the packet down the tunnel, at the other end, the receiving end will take the packet, take the hash, put the hash aside, calculate a new hash, compare the hash that was sent against the new hash that it calculated. If they're the same, we have integrity. But if somebody intercepts that packet, they can still read it. Aha. Now, in some cases, you don't care about the encryption. If somebody reads it, you don't care as long as it doesn't get changed. Now, why would somebody not want to encrypt? Because of the time it takes, the extra overhead. Encryption takes overhead. The routers have to do more work, and the packet gets bigger. The packet gets larger, the processing gets longer. So if it's a very time-dependent or a very slow link and security is not an issue, maybe all you need is the authentication header in the packet. ESP, encapsulating security payload, provides the confidentiality and the authentication. That provides your, hey, are you the right endpoint? But it doesn't necessarily supply the authentication. So ESP provides authentication and confidentiality, but not integrity. Authentication does provide authentication and integrity. You see, both of them, you always get authentication. But it's whether you want encryption or integrity. By the way, what if you want both? Then you have to apply both the authentication header and the ESP payload. And that's what it looks like. Authentication header provides authentication and integrity. ESP provides encryption authentication. And they say integrity, but in reality, that is not supplied unless you use both. ESP does not provide integrity, only the authentication header. So if you want both, you have to supply both. Does that make sense? Slight mistake on the slide. Very good then. So when we're building our framework, we have to decide what level of security we want. A combination of ESP and AH is the best option because that provides you with authentication, confidentiality, and integrity. If you use ESP, you only get authentication and encryption. If you use AH, you get authentication and integrity. You want both, you simply combine them. And by the way, that is almost always the standard. Confidentiality is provided. You select which encrypting protocol you want to use, DES, triple DES, or AES. Integrity guarantees that the content, so you select MD5 or SHA-1 or SHA-2. SHA-2 is more recommended. Authentication, how you're going to authenticate the two ends. And then you specify the Diffie-Hellman authentication group. There are several groups, DH24. Now, all you do is supply the group. All of this, 90% of the hard stuff is done within the protocols that are selected, but you've got to select the same protocols on each side. I really love this chart. This chart shows you what is going on. So the IPsec framework is this Lego environment. Now, for the IPsec protocol, the framework, you can select either authentication header, encapsulation security protocol, or better would be to have both. For confidentiality, you can have these. There's also a fourth one called SEAL. For integrity, you select MD5 and SHA. For authentication, you select PSK or RSA, and the Diffie-Hellman, you select the appropriate group. The trick is that whichever one of these you select and put it into the proper hole on one side, you've got to put the same in the other hole on the other side. So you've got to set up all the right cryptographic configurations on both ends. Now, if you understand the fact that we're just building this Legoland kind of environment, it does actually become pretty easy to do. Now, again, it gets a little confusing with all of the weird stuff you have to put in, lots of abbreviations, lots of protocols, and it can get very confusing. So a little chart like this can really help you out. Now, before I go on to the remote access section, I'm going to step back for a second and come out to I'm going to come back to my web page for just a second. I'm going to come back to the Academy site. And I'm coming down here. I want to come down to exercise and show you for a second. I want to come down to the exercise on IPsec. Now, this exercise is not going to give you enough information to know why you're going to be doing the things you're doing. It just walks you through the what to do. So what I'd like to do is spend a second and take a look at a couple of things on it. Now, this is a non-trivial exercise. Be prepared to spend a couple of hours because we're setting up two sets of tunnels. We're setting up a tunnel between R2 and R1 and a second tunnel between R1 and R3. Both of these are IPsec-based tunnels. I'm going to scroll down a bit. Now here, this is just making sure that we have the right level of licensing on our routers. So this is one of the problems you may have. If you tried to do this in, let's say, a NetLab, if you tried to do this on NetLab, I don't think that they have any 1900 routers in NetLab yet, which means you would not be able to do this in NetLab. You'd have to do it on live routers or in Packet Tracer. That's why it's a Packet Tracer exercise. Okay, so obviously what we're going to be doing is creating all of the appropriate traffic. So what the exercise does is walk you through every step, typing command by typing command. So step one is to identify the traffic that's going to be transmitted between the routers. That's your access list. Then you're going to configure the Diffie-Hellman configuration. That's ISAKEMP. ISAKEMP is the protocols that are used within Diffie-Hellman to create your shared keys, your secret shared keys. So they're walking you through all of these steps. So you're not necessarily, if you go through all of it, you're not necessarily going to understand everything that's here. And that's quite all right. You're not necessarily in this lab supposed to get every bit of how to set up IPsec, although it's a pretty good thing to know how to do. So what I'm going to do, and I did this for my class last night, and I'm going to post this one for you as well. I'm going to post on the site under the Files section. Under the Files section, there will be a document called Some Interesting IPsec Links. if you open up some interesting IPsec links, I have listed for you a whole lot of things you can read. They will take you through the details. They will walk you through a lot of the what is going on. Now, these are just some of hundreds of links that can explain this. For example, a very good one is this guy's right here. So over here, I have a blog from Darren Matthews. It's one of many. Like I said, you can look at any of them or all of them, and it will explain step by step exactly what you're doing when you're setting this up. The time tonight doesn't permit me to go through all of the operations on how to set these things up, other than to point you into some directions and give you some opportunity to read about it yourself. Call this a little bit of homework above and beyond what's in the normal class. I really, really suggest you spend the time to go through it in some detail. Go through all those links. I will post those right after the class is finished. Could we have extended this lesson into 2 parts? Probably yes. Probably yes. If I had thought about it, I might have, in fact, in a future semester, since the previous chapter was so short, would maybe to start this chapter last week and then finish it up this week and go into some extra detail. So yes, I could consider that. But to be honest, there's enough information in the chapter to get you through what you need to know about setting up a basic environment, because it's a big rabbit hole that you can start getting down when you start getting down into some of the real nitty-gritty of the protocols. So perhaps, given the fact that this is not really a security class, most of this stuff occurs in CCNA security. You get down, you really get down into it in CCNA security, because we're dealing with ASA devices. Yes, you can implement site-to-site VPNs using a 1941 or a 2901 router very easily. But most companies and most organizations will not use a router-to-router, but instead they will have a security appliance like an ASA appliance on both ends. The reason is it's a little bit easier to set up because you're in you can be doing it in a GUI environment. Also, the device is built to do it, so it's a little more effectively done. So they leave the discussion at it. Do you have CCNA security at OCC? Not at this time. No, sorry. Wish we did. Working on it. My sister college, Coastline, I believe, does have CCNA security. And I know that, for example, several of the colleges in Northern California have CCNA security, and I believe they even do them online. So that might be another option for you. No, CCNP is strictly Coastline Community College. We don't do CCNP. Instead, Orange Coast College does Juniper as their more enterprise-level routing courses, so as we don't have a too competitive of an environment with them. But thank you. Good questions all. Okay, so remote access VPNs. These are a lot of fun. Remote access VPNs is I want to access my network at the office from anywhere I am. I want to be at an airport. I want to be at home. I want to be in Cleveland. Actually, I don't want to be in Cleveland. But it doesn't matter. Are the Juniper classes online? No, they are hybrid. Half online, half on campus. So the remote access VPNs are there for you to be able to securely access your network. There are two ways of deploying these. One uses SSL, your standard SSL, and the other uses IPsec. Now, which is better? It depends. There is no rule that says one is better than the other. SSL is probably easier for the users, and SSL also gives you advantages that you don't necessarily need a dedicated client on your remote machine. For example, if you want to access a Cisco IPsec server, you have to run the Cisco AnyConnect client, which you'd have to download off the web, install, and configure, as opposed to the SSL, which means you just go to a website, give them your username and a password, and you're in. So it's a matter of convenience. There's some security issues and there's some usability issues, but we'll look at both of them in some detail over the next 10 minutes or so. The SSL VPN is becoming the preferred way because of its simplicity. Simplicity for the end user, not necessarily simplicity for the administrator configuring it. But it provides remote access, secure remote access, using a web browser. And the web browser's native SSL. So everything is running through port 443. Now, is that a good security encryption protocol? Yes, it is. Yes, it is. You can also use the SSL VPN if you want to use the secure client as well. Either way. The Cisco AnyConnect client using SSL, it's a standard client. You download it off a website. You install a piece of software. You run it as a service. You do all your setups. You write in the IP address of the endpoint. You give it username and password. You set up the security environment. You do all kinds. It requires some heavy-duty configuration initially. The clientless VPN, all you need is a web browser. Everything else is handled on the back end, on the server side. This is what it looks like. So the Cisco EasyVPN negotiates your tunnel parameter, establishes the tunnels, builds the tunnel, authenticates the users by username and a password. Very good there. Manages your security keys. Remember, you still need security keys. You still have to set up your key exchange. And it manages your encryption and decryption and integrity throughout the tunnel. Very, very straightforward. In order to build out the Cisco EasyVPN solution, you need a server. What's the server? It's a Cisco iOS router or ASA. So you can do VPN client, you can do remote access VPN if you have a router out there. It's easier to set up on an ASA appliance, but you can use it on a router. You have to have the VPN remote, which is a firewall. Now the firewall basically acts as your catch at the corporate office. All of the inbound activities from your remote clients are caught by the EasyVPN remote service. So VPN remote is a service running on the router or the ASA firewall. And it basically provides the catch for you. And then you need the VPN client, an application that is supported on a PC used to access a Cisco VPN server. So that's what you have to deal with. It's very easy to set up. We're not going to set it up in the class. We're just going to talk about it. So this is what you need to do to set it up. And this compares SSL and IPsec. So SSL is web-enabled, is primarily used for web-enabled applications. although everything goes through the tunnel. Everything goes through the tunnel. It works best if it's web-based stuff going through the tunnel. Encryption can be moderate to strong depending on how long your key is. IPsec is always considered to be stronger. Now, authentication can be moderate if you use one way, but if you use two-way, it can be much stronger. IPsec is always going to be stronger. It's extremely easy to use SSL to connect, whereas it's a lot more challenging to set up an IPsec connection. And in SSL, now it's any device with a web browser that supports SSL, but that could be your phone, it could be your tablets, it could be your television. Whereas IPsec can only negotiate with devices that have the Cisco client included. Michael, it's port 443, not just 43. Port 443. Or 443. All right, so just to quickly summarize, VPNs are used to create secure end-to-end private networks over any, by the way, they are used over the internet, but they can be created over any network as long as you can see the IP address at both ends. Site-to-site VPNs set up a tunnel between endpoints, and individual devices on the LANs at both sides don't have to know anything else about it. Remote access VPNs requires that software be installed on host devices that allow it to be the endpoint connecting to your VPN router or firewall as it goes along. Robert, yes.
On these VPNs, you said they could be from any network. Would the Pentagon be using VPNs within it because they need to know for certain secret information?
Internally within their LAN, would they be using VPNs?
Yes.
They might be, but my guess is that they're even going to go more secure than that, and they will put that level of secure traffic on its own network, on its own cables. Its own cables and its own switches. I would imagine that they're not even going to trust it to VPNs.
On security, it's mentioned that the most secure way is copper wire as opposed to wireless. But
very much so.
Yeah, when a signal is transmitted on a copper wire, there's certain magnetic waves that come off. Have these ever been captured?
I've heard stories about it. I've never actually read anything practical. And there's two things you can do. Number one, if it was unshielded twisted pair UTP that we use, you'd have to have your sensor probably within 4 or 5 inches at the most. And if it uses shielded, which is what they would use, nothing's getting out of that aluminum shielding. Or very, very little. You'd have to be within a couple of millimeters at the most. But they're not going to use, I'll guarantee you, they're not going to use wire. They're not going to use copper. They're going to use fiber.
Thank you.
Yeah, they're going to use fiber, which means there is no bleed off. Yes, Michael. Okay. GRE, which is the first thing we learned, is your basic tunnel. So the first thing we learned was how to build a tunnel, not how to secure it. So GRE is your basic non-secured site-to-site tunneling protocol. Do we use it for anything? Yeah, it's used to deliver some interesting stuff, but it's very, very seldom used, and it's never, ever going to be used in a secure environment if you want any kind of security whatsoever. Instead, we're going to create encrypted tunnels using the IPsec framework. Now remember, I'm going to emphasize that. IPsec is a framework that consists of a set of framework headers, whether it be encryption, authentication, integrity, or all three. It's going to be non-repudiation, non-replay or anti-replay. and it will have a very complex secret key exchange. The better the encryption, the better the confidentiality, or the more confidentiality requires better encryption. We talked about symmetrical versus asymmetrical encryption, secret key versus public-private key, and then we use the Diffie-Hellman framework, or the Diffie-Hellman group, to decide how we are going to get the two endpoints to exchange their keys. Yeah, Jonathan, copper can do 10 gig, but in theory you would have the same security issue. So while fiber makes a great way of going very fast, copper can still get up there. But fiber gives you a level of security, and distance, by the way, that you don't get with copper. So between distance and confidentiality, and the price of fiber has come down enough so that in a lot of cases, companies can afford to go that way if they need that either distance or extra level of confidentiality that exists. Okay, so questions, Michael?
Yeah. Now, can you hear me?
Yes, I can.
Cool. I couldn't make it work the first time. Anyway, I got twisted headset. Anyway, with all that said, the idea is, my question is, you said that the VPN can be done on any network, okay?
Correct.
So if I wanted to set up a VPN between me and another employer or something, and that would be like private messaging would be done through a VPN, is that correct?
Let me see if I understand what you're asking. You're saying if I was at a network at your office or at home, let's say I wanted to create a private network, let's say between two devices. And the answer is yes, you can. Now, that said, getting the software to run on two devices requires that it knows how to support a VPN endpoint. So typically, it's very easy to set up a client computer like a Windows box or a Mac to connect to a VPN server like a Windows server or a Linux server or even a Cisco router. But if you're trying to connect two Windows machines together as a VPN, then it would have to have the appropriate software to set up a site-to-site or point-to-point VPN. So the short answer is yes, you can do that. The longish answer is it may be a little more tricky simply coming up with the right software at both sides.
Okay, then maybe I'm asking the wrong question. Anyway, when I see a couple of employees having a private conversation through, say, text messages or whatever from within their own LAN, okay, it's obvious it's not leaving the LAN.
Right.
Anyway, they're having a private conversation. Is that done through VPN or is that done through a different thing? All of a sudden,
it's probably being done with what's called local encryption. So what happens is it's similar, but what you're doing is you're encrypting the packets before it leaves your device, and it's decrypted. It's a simple encryption decryption. It doesn't have the whole infrastructure of a
VPN.
No, it doesn't have the infrastructure. It's just encrypting data coming out and re-encrypting it coming back in. And that usually happens up at layer 6 of the protocol. It's not even happening.
Now I'm probably still not asking the question correctly. How's this one? Okay, so when I see on television, okay, that this guy's sitting there on his computer, and all of a sudden a message pops up from who knows where, okay, on his computer, unbeknownst to him, unsolicited by him, or what have you. What has this other guy done? How is he getting that message to the computer?
Oh, he just happens to know. It depends on what the software, but he just happens to know what the IP address is of that computer or the device name of that computer or a way to identify that computer, and he was able to send a message. Now it depends. Again, this is all happening up. That's what you're talking about is all application layer stuff.
Okay, so it's just a matter of having the right program.
Right. Or hacking a program that he has on his computer that you can basically take over.
I want to say okay.
Okay.
Anyway, okay then, thank you.
You're welcome. No worries. Okay, any other questions? Okay, for the good of the folks that are not here tonight, in addition, I want to get this on the recording, and that is we are down to 2 weeks prior to skills drill. I repeat, we are 2 weeks prior to skills drill. Next week we have a lecture covering the last chapter in the book, or the last chapters in the book. And that will be chapters, hold on, I will tell you in a second. So we have 2 more chapters, chapters 8 and 9, covering monitoring the network and troubleshooting the network. So 2 more chapters next week, and then the skills drill. So keep that in mind as we go along. You should be working on your chapter tests. You should be working on your labs. I have seen a lot of your labs coming in. I should have all of the labs that have been submitted graded over the weekend, so you'll have a good idea of where you stand there. Don't forget to do the practice skills-based assessments. Take the practice final exam to get yourselves all geared up and ready for the final. So, any other questions? I wanted to get that into the notes. 2 weeks before the skills drill. So next week we'll meet. And by the way, one more thing, I apologize. Next Thursday is Thanksgiving. Thank you, Jason just caught me. Next Thursday is Thanksgiving. Now, I am absolutely positive that all of you would just love to be here at 6 o'clock next Thursday. So you're all going to skip your Thanksgiving dinner and join me here. What? You're not? Hardly, Bill. No. The next lecture will be a week from Saturday at 8:30 a.m. We will meet as per our schedule, not next Thursday, but a week from Saturday, 8:30 a.m. online, where we will be able to partake in the last 2 chapters of the book. So I will I will make sure I send out an email announcement of it next week as a reminder. As we get closer to it, I'll send out a reminder so that everybody remembers. What's the date? That would be November 29th. November 29th. 8:30 a.m., the usual place. And we'll go probably till about 10 a.m. So we'll go from 8:30 till, no, I'm sorry, we'll go till about 11 a.m. 8:30 to 11, 2.5 hours. Just like we have the 2.5 hours reserved for our class here. Okay then. Everybody have yourselves a great week. I am not going to see you guys before Thanksgiving, or I'm not going to talk to you guys before Thanksgiving. So please have a wonderful Thanksgiving with your families, and drive careful. Be careful out there. Keep up with your work, but go ahead and take Thanksgiving off on me. So if there's no other questions or no other comments, I am going to stop the recording.
Recording stopped.
Okay, everybody have a great evening. I'll talk to you all next week. Actually, I'll talk to you in a week and 3 days.